Welcome to Radar System course. Today we learn FMCW altimeter. So we have seen earlier that FMCW radar, in which frequency modulated continuous wave radar we have seen, and that frequency modulated continuous wave radar that is useful to find out the velocity of the object, as well as we can use to find out the range there. Now if you see that a CW radar mostly it is used to identify what is the velocity there. But now we consider this radar, the FMCW radar, for measurement of a range as well as the velocity of the object there. But sometimes what happens if that object is fixed now, so in that case, how to identify those particular objects? Means they are not moving, objects are fixed now. Okay, there is no motion of the object, that is called a stationary object. So in that case, how to identify the object there? So only that reflected signal or echo signal from the object, that will define only the range, but we are not able to say that it is moving. Okay, so velocity we could not identify there. There are various ways to identify whether that object is stationary or a moving object, or our radar it will be a moving, or both are moving there, both are in motion. So we can obtain the range as well as the velocity of the object there. Now we talk about that altimeter. Generally altimeter is used to measure the height. Generally this altimeter is used in a aircraft, and that is used to measure the height above the surface of the earth, because we have seen that the object, if you consider that a aircraft, in that case the aircraft has a large cross section there. When we provide a signal from the radar here, okay, when we say that signal is transmitted to the radar, so large, because of that large cross section, the signal get reflected from this. For example, if you consider that instead of a radar, we are supposed to consider there is a surface, so we will get that that altimeter is available in a aircraft, that will send the signal here, so that that height from the surface can be measured. Okay, so we can consider that a height from the surface, or we can use this for the measurement of the velocity there. Now in both the case, if you consider here whether we send the signal from the radar or whether we are sending the signal to the ground surface from this device, aircraft, so the surface looking from this end will be larger, from this end it will be larger. You can say that it has a larger cross section, so that we are able to identify that height from the surface there. If supposed to be aircraft is in motion, so in that case, so that surface as compared to the aircraft, it is not in motion, it is fixed one. So in that case, the difference of the motion, if you consider here, from the aircraft in terms of motion is very very small. So because of that, there will be a Doppler shift from the surface will be a very very small there, or we can say that a Doppler shift will be neglected there. Now this FMCW radar altimeter, or we can generally say only a radio altimeter there, that is to be operated in the band of 4.2 to 4.4 gigahertz. This band is fixed to measure the height from the surface by the aircraft, and that band is reserved only for the radio altimeter there. Now if you consider that when a landing occur, okay, for the aircraft at the time of a landing, so that aircraft is looking for the surface, how much is the height, and in that case that radio altimeter mostly suitable or mostly used at the time of a landing of the aircraft there. And if you compare that height at the time of a landing, it is very low, okay, as compared to the height while traveling. Okay, so in that case, if you see the device we are using in the altimeter, mostly we say that a transmitter. So it not require a large transmitted power because that height is a small, as well as that cross section is a large there. So even if we send a small signal power, so that small signal power can be scattered from that a cross section, so we'll get the a echo there. So that's why we can say that radio altimeter that are used in low power amplifier or low power devices. Probably if you consider that the klystron and magnetron, they are large power devices, but we can use a solid state device instead of a klystron and magnetron to generate the power at a radio altimeter there. So now, what are the various components in the CW radar that we will see here? So we can consider that a transmitter and receiver earlier, and we have seen that there is a magnetron or a klystron at a transmitter, and at a receiver side, that receiver observation will be a homodyne, heterodyne, or a super heterodyne case there. So now in the case of a radio altimeter, generally we require to measure the height properly. That's why your receiver is to be more and more sensitive. For a more and more sensitive receiver, we are supposed to use a super heterodyne receiver there. Now, for the transmitter, we can consider there may be a solid state device, but at the receiver, a super heterodyne receiver structure is to be used. So homodyne and heterodyne, we know that homodyne is directly to the modulator, and a heterodyne, we are using one mixer. And if you consider that a super heterodyne case, we are supposed to use a two mixer there. So that's why it is called as a super heterodyne receiver. Now we go ahead here a discussion on how this FMCW radar or FMCW altimeter components there. Now it has, we consider a transmitter because we say that it is about FMCW altimeter. So we can consider that this is nothing but your FM transmitter. And this one is about your modulator. And then at a receiver, we are supposed to provide the timing, because what will be the time or at what time that signal is supposed to be transmitted. So that's why we should have to provide the timing information or a timing signal. Then whatever the transmitted signals are there, for this particular transmitted signal, some sort of a portion of transmitted signal that is to be applied to the mixer, that is that will generate a oscillating signal for the receiver mixer. We consider here mixer now. This one is about a transmitted signal. After that, we consider that a local oscillator, and here it is just like a sideband filter. Then we have a mixer. That mixer is for the receiver. This one is the mixer for the receiver. Then we have the antenna for the receiver. Now we are getting a modulated signal here. That modulated signal that is transmitted here, we are making that isolation between the transmitter and receiver. So separate antenna for the transmitting and the receiving purpose, that is to be used, so that isolation at the receiver because of the transmitted signal takes place there. Now here we consider that a mixer, so portion of the transmitted signal that is to be applied to the mixer, so that we'll get the bit frequency signal at the mixer and a mixer at the receiver. So that will reject the whatever the component from this filter we are receiving. So generally this one is about a sideband filter. So we are getting that a mixed signal to the at a mixer here. Now for example, if I suppose to write in terms of a frequency and all, so we have a transmitted signal here, that is about ft now. Here we have a transmitted signal, and here we consider that a local oscillator signal. But at a mixer, we supposed to get the two components. One is about ft plus flo and ft minus flo. So mixer is providing the component that is about, generally difference component is propagating. So you can say that it is about ft minus flo at this mixer point. So generally we say that there are the two components, ft plus flo and ft minus flo from the mixer. So we supposed to use a sideband filter, so that we are getting at this point, at this moment, ft minus flo at a sideband filter. So filter select only the component that will be, we can consider that ft minus flo. So in terms of a band, we say that is about a lower sideband, because a sideband filter is there. So sideband filter, so we can supposed to be right here. So we have the signal that is to be transmitted here, and we have a two signal. One is about ft minus flo and a ft plus flo. So now it is to be considered only that this particular component at this sideband filter there, and this component, highest component, that is to be rejected by the filter there. Then if you consider the a bandwidth here for the given particular filter, so bandwidth what we have considered at a transmitter for this FM transmission here, so similar bandwidth is supposed to be considered at a filter, so that that particular band of a component is to be passed through the a filter there. Now then we are getting the Ft minus FLO here. Now that is a signal to the mixer, and that signal at a mixer, that is to be act as a local oscillator signal there. Okay, means you can say that this one is about a input to the mixer. So generally for a mixer we are supposed to provide a some frequency signal to remove that particular band there. So in that case this will be act as a sideband filter, is act as a mixer. Now that particular signal, if you consider here, it is to be passed through the mixer, and we are getting the echo here, and that echo is nothing but whatever the transmitted signal we are supposed to transmitting here, and that will be at f of t we are supposed to transmitting the signal. So that's why we are getting the echo after small duration. So that's why we can say that f of t minus t. Okay, that is about the signal at the receiver. That is about the echo signal, and that signal, and here Ft minus FLO, we have the transmitted signal here. So at this point here, we are getting that a signal that will be difference of this Ft minus FLO we have earlier we can supposed to consider, and we supposed to consider that Ft minus T. Okay, so at that particular moment. So in that particular case, we are getting that this signal as well as the whatever the transmitted signal. So means Ft minus here at this moment here, f of t minus t here minus f of t. Okay, so that is about it, the signal we are supposed to be getting, and that signal frequency is called as a bit frequency. So at this moment, okay, at that particular place, we are supposed to get that a bit frequency signal. Okay, we are supposed to get a bit frequency signal plus whatever the we have the a local oscillator frequency signal that is to be passed through the a IF amplifier. We have the IF amplifier here, because echo signal we are getting at the receiver at this particular antenna. So it has a frequency signal, that is a Doppler shift, as well as a range signal. So means we can say that that signal we are getting at this particular moment. So it has a range frequency as well as a Doppler frequency. So now we need to identify that what will be the this optima this one. It has a Doppler shift as well as a range frequency, and that is called as a your a bit frequency signal. Now what will be the Doppler shift and what will be the range frequency signal, that can be identified using the another detector we supposed to be used here. Okay, so now again we supposed to consider that a balanced detector here, This one is about a balance detector, and we are supposed to give the some sort of a whatever the local oscillator signal here, FLO, from this IF. Now here FLO here, and FLO FB plus FLO here. If we have a FLO here, that FLO we are getting only the FB signal, that is about a bit signal. Bit signal consists of a range frequency signal, that is FR plus whatever the FD, and then that is to be applied to the low frequency amplifier. We have a low frequency amplifier, and then some sort of a input, it is to be given to the identifying whether it has a range as well as the a velocity there. So to identify the range, we are supposed to consider that another component to find out what will be the frequency there. So that's why we are supposed to use a frequency counter here, average frequency counter, and that average frequency counter will provide you what will be the range here. Okay, and will provide you what will be the range of the a signal, and then some sort of a portion that is to be applied here to the switched frequency counter. Whatever the change switched to frequency counter, so that we'll get that Doppler shift there. So that's why that Doppler shift will use to find out the what will be the velocity. Okay, so that is about it. You can say that a Doppler velocity. Okay, so now we can identify that from this, whichever the echo signal we have received at this. Okay, so we are supposed to consider that some sort of a transmitted signal portion, and here, as I told you earlier, we consider that some sort of a timing signal that is to be used, because to find out what will be the okay. So this is about your a timing information. This is about a timing signal. Okay, so that timing signal that is used to find out the velocity. Now, if you consider at this particular point here, so we are getting a bit frequency signal. That bit frequency signal from this okay mixer and all, we have a bit frequency signal that is supposed to be passed through this IF only for a specific band there, and then it is to be passed through the balance detector. Means it is amplified here, IF signal amplified, and that is to be given to the balance detector. And that balance detector means what? It has a FB plus local oscillator frequencies, and then output of that particular detector, it contains that bit frequency signal FB, and that bit frequency signal, if you apply that bit frequency signal to the, that is to be amplified first, and then it is to be applied to the frequency counter, and through that we are able to obtain the what will be the range of the target and what will be the Doppler velocity there. Now, what will be the target here in that case? So target at what particular place? Okay, what will be the range here, whether it is a short range or a large range there? So that will be depending upon that what will be the level of the signal we have received. In the case of a short range there, if the level of signal is large, you can say that we can consider that that level will be, that range will be a small, means okay height. Okay, if it is a height is a smaller there, So in that case, the signal level will be large there, means strong signal we are getting, okay, from that. If supposed to be a long range is there, so then in that case we supposed to get that a weak signal, okay. Now that a strong signal and a weak signal at a low frequency as well as a high frequency we supposed to be get there. So in that case, if you consider that, what is the frequency of operation of this altimeter? So generally for a low frequency we supposed to get the small range, and for the high frequency we supposed to get the a large range there. Is that signal level is about a signal strength will be high or signal strength will be low there. Okay, so in that particular case we consider here. So low frequency signal that corresponds to the a short range, and it has a large echo signal, means large power. Okay, that signal level will be large there. So in that case, we are supposed to apply the attenuation at the input side. So that's why we need to provide a attenuation at a low frequency, but at a high frequency, when we wanted to apply the attenuator there, so in that case, a echo signal we have received because of that large range, that will be weak. So that's why we supposed to apply the low attenuation there, or no need to apply the attenuation there. Now this one is about the signal we have received from the target or object, but supposed to be, if there is a stationary target, or we consider that there is a clutter, so how to identify that a signal from the clutter and all. So there will be a shift at that particular place, will be a small, and signal strength we can identify easily as compared to the what will be the power received. So generally we say that a higher range, smaller, okay, or a larger range, we supposed to get the weak signal or a high signal. Okay, okay, low level signal or a high level signal. Power level will be larger or a power level will be small. So based on this power level, we can consider that that particular device, okay, as per the particular power level, we can consider that the echo we are receiving from the target, that will be nearer or that will be away from the radar there. So in that particular case, when we consider that a signal we are getting from the object, it may consist of some noise, okay, echo. It's not the echo from the only the object, or sometimes we are getting the signal from the different area, okay, that scattering angle and all. So that's why in that case we supposed to get the a signal will be a weak there. Now that weak signal supposed to be a part of a noise we supposed to consider, because if that range is a small and we supposed to get a high level signal, okay, strong signal from the small range. But even if we are getting a, a small signal level also in that particular range, and that particular signal is supposed to be considered as a noise there at the receiver, and that noise is from the any other object, okay, because we consider that the range is small. If the range is a large, So in that case, we are getting a low level signal, and then it is difficult to identify the signal as well as the noise there. So we consider a filter at a, we can consider that a lower side band and upper side band, so that we can easily identify or easily differentiate what will be the a noise at this particular. So we need to suppress it from the given end, from that particular end. So that band of operation for those devices we are using, if it is limited, so in that case we are supposed to suppress the a noise from the any other sources, or we can say that any other sources we are getting the signal at the receiver there. So another way we can find out, instead of saying that there will be the received echo signal from the other object, so we can consider another way to identify that the height of the object, okay, the target there. So we can say that a narrowband filter we supposed to use, or we supposed to consider that a signal transmitted from this transmitter, as well as that level we are receiving at this receiver there. So in that case, there may be a small variation in the frequency there. So in that case, what will be the deviation in the frequency? And that deviation of in the frequency that can be used to identify that what will be the range of the a signal there. So sometimes errors occur while measuring the height there. So in that case, if a small error is there, for example, we supposed to consider that aircraft is landing, and in that case, while measuring the height, there will be a small error. So then it will be difficult to land that aircraft there. Okay, so then we can say that at that particular situation, so blindly that aircraft is to be land. So in that case, we need to reduce the error. So there we should be a accurate range is to be measured by the device there. And what will be the a signal to noise ratio at that particular beat frequency signal? So that is to be measured here. And generally that difference of the frequency, it is inversely proportional to the what will be the range there. And we can consider that a bit frequency is varying, because we say that there will be a range as well as there will be a Doppler shift. Why it is varying? Because that range is changes. Okay, so it is continuous one. So in that case, that FR will be changes as well as the FD will be changes. So in so at that particular moment, so there may be a small variation in the range occur, and due to that there will be errors for measuring the range and all occurs there. So what will be the exactly error while we are transmitting the signal? So transmitting signal, we are receiving the echo, then we are having some noise there, as well as at the receiver we are measuring the frequency. Okay, we are measuring the frequency, we are supposed to use a frequency counter there. So that frequency measuring device that is used to measure the what will be the cycles are there. So how many number of cycles in a given particular period of a time or we can say that a modulation period. Okay, so that total cycle count measured by this particular counter, that is that will provide you, so what will be the accuracy. Okay, so at the time of moment, at what particular moment we supposed to start the measuring, or what will be the cycle time, so that whatever the variation in the cycles measurement, and that variation in the measurement, that will be changes based on that modulation timing, and because of that we are getting that fr and a velocity there. So how many number of cycles measured by the device, because of that there will be error at the frequency counter, error at the receiver, that is signal to noise ratio at this particular place, as well as the error at the measuring the frequency counter, that is about the range. So what will be the number of cycles there for the given particular beat frequency signal in a one modulation period? Okay, that is about whatever the modulation cycle FM at the transmitter there. That's why timing information they are provided. So that is nothing but what, depending upon that beat frequency signal and a AFM. So we can consider that the number of cycles, okay, number of cycles here is equal to what? A, what will be the average number of a beat cycle or a beat frequency in one modulation period of a cycle. So that's why you can say that FM average. Okay, this one is nothing but the average. So now what will be the range here? So in that case, so we can obtain the range here. Okay, so we can obtain the range here. That range is equal to range R is equal to what is the velocity. Okay, that is about velocity of a propagation there. See, n is nothing but a number of cycle 4 to del f, and that is about a frequency of a expression, and that is to be obtained by varying the a bit frequency. Means we are getting that delta f based on that a bit frequency there. Okay, we need to maintain that a frequency of excursion, so that we will get a bit frequency there, and we supposed to reduce the a signal to noise ratio. So this way we can obtain the a range there. Now what will be the error? Because we are supposed to measure the count of the particular frequency signal, so there may be a error in a range, and that is that error based on that a frequency counter there, and that error is called as a quantization error, and that quantization error, it is equal to, we can consider that del r here is equal to c by 4 del f, or we can write in terms of a frequency also, because c is nothing but what will be the velocity of a propagation there. In that case we can obtain the excursions and all. So sometimes we are getting that at a receiver some unwanted signal. That unwanted signal is nothing but what? There will be a transmitted signal, okay, and that transmitted signals are reflected by any other object. So that's why we are getting the at a receiver small mismatch occur here, or we can say that echo signal we have received because of that echo signal. Okay, so at this moment there will be a noise here, and the noise or at the time at a measurement there. Okay, so this one is about a noise, and this one is about the error at the measurement of the range and all. So this one is about a FMCW altimeter that is used to measure the height of the object. So we can consider that what will be the mixer frequency and what will be the bit frequency there, and that is to be used to measure the height of the object. So next we are supposed to consider that a multiple frequency CW radar. So we have seen that a CW radar earlier. So in a CW radar we have considered earlier that is used to measure whatever the echo signal we are getting. Okay, so from that we are supposed to measure the a range there. Okay, so generally that a CW radar is used to measure the velocity. Okay, so even we can use to measure the what will be the range also. Okay, so we can consider that what will be the a difference in the frequency or a phase, okay, received at the echo signal. Through that we can measure the what will be the velocity as well as the range of the object. So generally CW radar is not used for the measurement of the range there. It is to be used for the measurement of the velocity. But if you consider that a multiple frequency CW radar, okay, so instead of a CW radar, so we can consider that a multiple frequency CW radar. And that multiple frequency CW radar, that is to be used for the measurement of the range as well. So in that case, we need to measure the phase of the echo signal relative to the what transmitted signal we supposed to be transmitted. So we need to differentiate the phase of the transmitted signal and the echo signal. So generally a phase if supposed to be difference is beyond the 2 pi. In that case it is difficult to measure the range of the frequency. So in that case what will be the ambiguous range? What will be the unambiguous range? So if we supposed to get the measurement within a 2 twice pi of phase difference, that in that case that range will be the unambiguous range. If it is beyond that, then ambiguous. So already we have discussed that a ambiguous range and unambiguous range, that is defined for only the pulse. When we transmitting the pulse is there, so when we supposed to receive the echo signal before transmitting the second pulse, so in that case we are getting the unambiguous. If we supposed to get the echo signal after for transmitting the second pulse, then in that case that will be the ambiguous. So we consider that. So what will be the transmitting signal in that case? So generally, if you consider that a CW radar, so it radiating a single signal frequency signal, and that is about a sinusoidal signal. So we can write here sine of twice pi f0t. Okay, in that case can consider in another way also, omega 0 t. Okay, omega 0 is nothing but twice pi f 0 here, and this particular signal is to be transmitted to the given target at a given particular range, and then the target, when that signal reaches to the target, then echo occur. Okay, that means it will be reflected from the object then, and then the same signal will be returned to radar after a given particular time. In that case, we say that a target range is supposed to be r. We are getting the signal, there is nothing but a range of a target here. We consider that this one is about a radar here, so it has an antenna now. Okay, we are supposed to consider the target. Here we have the object now. So we are supposed to transmit the signal, and we are supposed to receive the signal here from the object. So in that case, this will be the range. And we received the signal at a given particular time. So that's why t we can define twice r by c. And c is nothing but the velocity of a propagation. So that velocity, this one is about a transmitting signal, and echo signal received at the radar, that will be what, difference in the time, because a small variation in the time. So that's why we can write here sine of twice pi f0. There is a difference in the time t minus t. Okay, that is about the echo signal we have received. So from this we can find out for the echo signal what will be the phase difference there. Okay, suppose I say that difference in the phase between the two signals, that will be a twice pi f0 t here. So in that case, it is equal to what? 4 pi f0